Everyone, welcome to the HSC Chemistry lecture. So I'll start off by introducing a little bit about myself. So my name is Thamika, and I'm a ex-North Sydney Boys graduate. I graduated in 2022 with an ATOP 99.30. I got an HSC Chemistry mark of 97 out of 100, and currently I'm studying medicine all the way in Queensland. So yeah, pretty far away, but yeah, I'm enjoying it currently. And my a bit about my hobby. So I like playing piano. I am quite hooked on Valorant right now, and I'm also quite a fan of Bed Wars, which is like Minecraft basically. So yeah, that's a little bit about myself. And now just a quick bit about ATAR Notes. So since 2007, we've been offering heaps of free resources to make sure students like you can thrive in their studies. So we've offered free lectures, just like this one, since 2015. These free lectures are in line with ATAR Notes' mission to help students as much as possible, and we have tons of free resources for you. So as you can see here, we have the study notes. So here are just a couple of things that we offer you, and you can find pretty much everything at atarnotes.com. And if you want more tips and info on how to use these resources, you can check out the info doc underneath the resources section of this lecture page. And yeah, we have free notes, we have free videos, newsletters, and also a Q&A discussion. So if you have any questions about the content that you're covering, you can ask it in the online Q&A section, and then either current students or past students like me can answer your questions. It's a very helpful and supportive area as well. And if you're looking for even more, we offer some premium resources as well. So we offer low-cost group and private tutoring from TuteSmart. We also offer printed study guides and online access to study resources with Ed Unlimited. So yeah. And finally, I'd like to thank our sponsors for allowing for this lecture to be made possible. And yeah, with that out of the way, let's get into the overview. So today, or this lecture, we're going to be studying Module 7. And Module 7 is a pretty big content-heavy module. So we're going to be splitting it up into 6 sections, right? And the first section is quite important because the first section allows you to talk about all the rest of the sections. So we're going to be going through naming organic compounds, and then the safety and the economical aspect of organic compounds as well, alcohols and hydrocarbons and the different reactions that they go through, and other organic compounds and the different reactions that they go through. And then we're going to finish it off with some bit about polymers and soaps. So I think after naming organic compounds, I think the most important thing, in my opinion, is probably number 3 and 4. So the reactions that they go through. In terms of polymers and soaps, in terms of polymers itself, it's a lot of memorization. So you need to be able to understand a lot of the different polymers that you learn. So there's a couple that you learn in Module 7, and you need to be able to understand them very well. Naming organic compounds, in my opinion, was quite fun. And so we'll be going through that first. And so yeah, let's get right into it. Another final disclaimer is that obviously, since this is a 2-hour lecture, we're not going to be able to cover everything in very great detail. We're going to be condensing the entire module into 2 hours so that you get a very good idea of what you'll be expecting in Module 7. So that is kind of the expectation for this lecture and the outcome of this lecture. So let's get right into it. So, naming organic compounds. So the first thing that we need to know is the difference between an organic and an inorganic compound. So most people in chemistry up until now will have done inorganic chemistry. So that's with things like metals and salts, right? So table salt, NaCl, metals such as silver, iron, those stuff, they're all inorganic. Organic compounds are carbon-based stuff. So things like us, for example, we are carbon-based organisms. So like we're built on a carbon backbone, and that's kind of what makes us organic compounds. So organic chemistries, we're going to be dealing with a lot of stuff with carbon in it. So that's the main differentiator. So now that we know the difference between organic and inorganic compounds, let's go into a little bit more detail about it. So basically, when we're thinking about organic compounds, anything contains like a lot of carbon bonded to hydrogen, right? So that's the essence of an organic compound. And it is a massive subdisciple of chemistry, and there are around like 9 million something around 9 million organic molecules known, and even more being found out. And the most common or compounds are HONsP halogens, and these are the ones that are most commonly found bonded to organic compounds, and it's all because of the presence of carbon. So what's special about carbon is that carbon has 4 valence electrons, and so it can form 4 strong covalent bonds. So this is something that's very important and you should keep in mind for later when we learn about different organic compounds. And because of these 4 strong covalent bonds, it can come in many forms. And so because of this, they can bond together in rings and chains, and these form like essentially the organic compounds that we'll be talking about in this lecture. So the first thing that we'll be learning about is a thing called functional group. So there are different types of compounds that you have learned. So in school right now and in class right now, you guys might have looked at or maybe come across acetic acid. So, all right, CH3COOH. So if we look at if we're trying to name this using the proper, what we call it is IUPAC nomenclature. So if we're trying to name it using that, we look at what functional group it is, and obviously, since we haven't learned it, it's going to be quite difficult. But the functional group for acetic acid is carboxylic acid. So acetic acid that you know of is actually ethanoic acid, which is pretty cool. So CH3COOH is actually ethanoic acid. So there are a couple functional groups that we see here, and you don't need to know all of them. So alkane, alkene, alkyne, alcohol. You also have the haloalkanes, the aldehydes, the ketones, the carboxylic acids, the esters, the amides, and the amines. So those are the main functional groups that you'll be covering in Module 7. So let's go into the prefixes. So you might have noticed that when I said, instead of acetic acid, I said ethanoic acid. So you can see here that the prefixes that I used is eth. So that refers to the number of carbon atoms within a chain of the compound, the organic compound that we're looking at. So we have meth, eth, prop, bute, pent, hex, hept, and oct. And that all depends on the number of carbon atoms in the longest unbranched chain, or the parent chain. So let's look at, so we can see over here, right? So we have, now we'll look at alkanes, and we'll look at the prefixes for alkanes as well. So properties of alkanes are they're saturated hydrocarbons, and by saturated it means that they only have single bonds. So all the bonds that carbon could possibly form, are formed. So the maximum amount of atoms that could be within that molecule are within that molecule. So they're all single bonds. And the suffix that we use for this is ane. So alkanes, we ended with ane. And the chemical formula is CnH2n plus 2. And this is like what you can use to find out whether it is an alkane or not, or whether it could possibly be an alkane or not. So now if we look at the prefixes that we saw on the previous slide, we have meth, eth, prop, bute, pent, hex, hept, oct. We can see here we have methane. So we're using the suffix now because the functional group of this compound is an alkane. So it's an alkane functional group. So we have methane, ethane, propane, and you can see here C3H8. That follows that formula of CnH2n plus 2. And it also shows us that propane, which if we look here, prop, number of carbon atoms, 3. If we look at the compound propane, the number of carbon atoms in the longest unbranched chain is 3. So we have heptane over here, and the number of carbons in the longest unbranched chain is 1, 2, 3, 4, 5, 6, 7. So 7 corresponds to heptane. Same with octane, hexane, pentane, all of them. So that's what the difference between the prefix and the suffix is, and how we use the prefix. The prefix shows up most, if not all of the time, and the suffix shows up depending on what the functional group is. So the suffix often changes because we look at different functional groups. Like if we go back here, the different functional groups of alkane, alkenes, and alkynes. But the prefix always stays. So this is a little bit about alkane. So now we'll have a go at naming the alkane. So what is this compound? So let's go through the steps, right? So we want to find the prefix initially, right? Or we'll first look at the functional group. So if we look at the functional group, this is a saturated hydrocarbon. And we can say it's saturated because it only has single bonds, right? So the maximum amount of atoms that could be bonded to this organic compound is bonded to it. So only single bonds, saturated. Now, what do we know about alkanes? They're all single bonds and they're saturated hydrocarbons. So this functional group is an alkane functional, or like that. It is an alkane basically. Now that we know it's an alkane, what we also know is that the suffix of this compound is ane. So this compound, the name of this compound ends in ane, right? So now we need to find out what the prefix is. So for the prefix, what we do is we look at the longest number of carbon atoms in the longest unbranched chain, so the longest chain of carbon atoms. So if we count this now, we have 1 here, 2, 3, 4. So the longest carbon chain here is 4. Now if we go back, what is 4? 4 is bute. So we have the prefix and we have the suffix, and we put them together, we get butane. So here, the longest chain is 4 carbons, so the prefix is bute, functional group is alkane, prefix is ane, and the name where you put it together is butane. So that's how we would name an alkane. This is essentially like how we name most, if not all, of the organic compounds that you learn in Module 7. So now a bit of a challenge question. What is this compound? So like initially, like right off the bat, we can see that it's not going to be an alkane because it has a double bond. And one of the key properties of an alkane is it only has single bonds. So if we go back now, what has a double bond here? An alkene has a double bond here. An alkene has a double bond between 2 carbon atoms. So this functional group is probably going to be an alkene, and we haven't learned how to name alkenes yet. So one thing that I will say is naming things like alkanes, naming saturated hydrocarbons are a lot easier than naming unsaturated hydrocarbons. So alkenes, because they don't have only single bonds, they're unsaturated hydrocarbons. So to name this, right, we know what the functional group is, and just like alkanes, the suffix of an alkene is going to be -ene. So this compound will end in -ene. And we'll look at the double bond here, right? So we know it's alkene. Now we need to look at the prefix, right? So the longest chain of carbons, of unbranched carbons. So we'll look here. 1, 2, 3, 4, 5. So it's 5. And the prefix for that is pent. So it's going to be pentene. But we're not done yet. It's not just pentene, because if you can see here, right? There's a lot more variation, right? The double bond could be here instead of here. And we can't just call both of them pentene, right? So we need to specify this pentene from a pentene with a double bond over here. So the way we do that is we look at which bond the double bond is in. So it's in the bond 1, 2. So it's in the second bond. So what we do is we call it pent-2-ene, because the bond is located, the double bond, or the functional group, the double bond is located in the second bond. So if we look here, right, the longest chain, 5 carbons. So our prefix is pent. The functional group is alkene because of the double bond between 2 carbons. The location of the functional group is in the second bond. So 1, 2, second bond. The prefix, because the functional group is alkene, the prefix is -ene, and so the name is pent-2-ene or 2-pentene. Different ways of naming it, both are correct. I prefer pent-2-ene, that's just how I wrote it, but my friends have written 2-pentene, it's just the same thing. That's how we would do it. So now let's go into a little bit more in depth about naming alkenes and alkynes. So alkanes, alkenes, alkynes have very similar naming conventions in that their suffixes are they follow the same pattern. So for alkenes, the suffix is -ene, and the chemical formula is CnH2n. So for alkanes, it's H2n plus 2. For alkenes, it's H2n. So CnH2n. And then, yeah, they're unsaturated hydrocarbons, and they have at least one double bond between the carbons. For alkynes, there are also unsaturated hydrocarbons, and they have at least one triple bond between the carbons. So the alkyne is common between the due to the triple bond that exists between the carbons. And the prefix again comes from the number of carbons in the longest carbon chain, and the suffix is -ine. So the chemical formula CnH2n minus 2, that is the chemical formula for that. Couple side notes now. So the electron density of the double bond makes it more reactive. So it makes it more reactive than an alkane. So the electron density of the double bond and the triple bond makes it more reactive than the single bond within the alkane. We don't need to worry about it right now, but just keep that in mind. Alkenes are unsaturated since a double bond can flip out and bond to another atom. So if the double bond did flip out and bond to another atom, then the alkene would all of a sudden become an alkane. So if that double bond flipped out and connected to another hydrogen, then the alkene would become an alkane. But if it connected to anything else, it would not become an alkane. It would become a saturated hydrocarbon that's different to an alkane. Because an alkane is pure, right? It only has carbons and hydrogens in it. And another thing is things like methene and methine, they don't exist because it's just one singular carbon atom, right? So we can't have a double bond or a triple bond within a singular carbon atom. It just doesn't work. So yeah, because the definition is one triple bond between carbons, and if there's only one carbon, then it just doesn't work. So there's no methene or methine, it's just methane. But for alkenes, we have ethene, propene, butene, pentene, hexene. Obviously, we'll have to specify where the double bond is. Same with alkynes, we'll have ethyne, propyne, butine, pentine, hexine. And it goes all the way up as well. So that's naming alkenes and alkynes. So now we're going to go through the part that I mentioned before of how to find out where the bond is, how to specify which type of butene it is. So the IUPAC name for an alkene depends on, or an alkyne as well, depends on where the double bond is. So we number from the end closest to the double bond. So if there are 2 double bonds, it becomes a diene, so a penta 1,3-diene. So we need to have a prefix before the ene as well. So if there are 2 double bonds, it becomes diene. So we'll look at this now. So 1 but-1-ene or 1 butene. That's because it's bonded to it's in the first bond slot. So it's in the first gap between the 2 carbons, and so it's but-1-ene. Now we have but-2-ene because it's in the second gap between the 2 carbons. So this is called but-2-ene or 2-butene. Now we have this carbon. So in this one, if we counted one, two, three, it's in the third gap between the two carbons. So we should call it butene, right? But actually, butene or butene is actually not a thing, because if we just flip this compound around, can you see how this bond over here can also be considered as the first bond slot between the two carbons? So this like molecule could just be this initial one over here, because we all we have to do is flip it around and it'll be the same one as one butene or butanene. So what we have to do is, so we have to think about the symmetry as well. So if we can just flip it around and three butene will turn into one butene, obviously there's no need for three butene. So that's why we have the lowest number, and we have to make sure that that it can't just be flipped around. So we need to make sure that it has the lowest possible number. So we can't have three butene, because the lowest possible number for three butene is one butene. So we need to make sure that it's written as one butene. So always check to make sure if you can change if the numbers change depending on which angle or which line of symmetry you're looking at it from. And the convention is you don't have to count from left to right. So over here, for this molecule over here, if we count from left to right, we go one, two, three, and we end up with three butene. But if we count from right to left, we get one, two, three, and we end up with one butene. So we count in the direction that gives us the lowest number. That's also another way of thinking about it. Yeah, so going here, I'll make it a little bit more evident. So we have, again, so if we look over here, one, two, three, four. So four carbons in the longest chain, a triple bond over here. So it is butyne. Now we need to specify what type of butyne it is. So we look at the carbon, the triple bond, and the triple bond is in between the first and second one. So it's in the first bond slot. So it's but1-ine. So now if we look at the rightmost compound, we have one, two, three. It's in the third bond slot. So as I mentioned before, a couple of slides ago, you'd call it but3-ine. But now that we learned how to name where the double bond is, and how to name specifically what compound we're looking at, we know that this is also but1-ine, because in reality, if we flipped this rightmost compound over, so if we flipped it, it would just look like the leftmost compound, which is but1-ine. So we number it the lowest possible number possible, or you can think of it the way of flipping the compound around to see if you can number it in a different way. And we always end up with the lowest possible number. So that is the trick for IUPAC, or that is the rule for IUPAC. So both of these are but1-ine. So yeah, a quick summary of alkanes, alkenes, and alkynes. So alkanes have a single bond, and they're made up of single bonds, or the key thing for them is that they're made up of single bonds of only between carbons and hydrogens. So the structural formula is, structural formula is, C. So if we're doing two carbons, the structural formula will look like this. So CH3CH3, and the molecular formula is CnH2n plus 2. For alkenes, what makes them special is the presence of a double bond between two carbons. And if we're going to do it for two carbons, we get ethene. So for ethene, we don't need to specify if it's eth1-ene or eth2-ene, because there's only one bond between the two carbons. So no matter where the double bond is, ethene will always be ethene. So we get molecular formula as CnH2n. For alkynes, what makes them special is the presence of the triple bond. So we get ethyne, so CnH2n minus 2. So that's a summary of alkanes, alkenes, and alkynes. Now we get into the next functional group, which is alcohols. So this functional group, the hydroxyl functional group or the OH functional group, the prefix comes from the number of carbons again. The suffix this time isn't ane, it's ol. So it's like alcohol, it ends in ol. So the chemical formula is CnH2n plus 2 OH, or CnH2n plus 2 O. So yeah, so if we're looking at, there are a couple of different types of alcohols, right? So we can go back to the prefix again. So if we look over here at methanol, ethanol, and propanol, we can go back to the prefixes, right? So we look at the longest number of carbon chains. So for propanol, we look at the longest number of carbon chains, we get 3, right? So 3 is the longest chain of carbons. Because of that, the prefix is prop. And then the suffix is, we see the presence of an hydroxyl function group, or an OH, right? We see that, and we realize now that this is a hydroxyl functional group. So we see the OH, we realize it's a hydroxyl functional group. And so we know it's an alcohol. So now it becomes propanol. So if we're labeling this, methanol, propanol, ethanol, butanol, pentanol, hexanol, heptanol, octanol, that's how it would go. So another thing is, there are 3 different types of alcohols. So we have primary alcohols, secondary alcohols, and tertiary alcohols. Primary alcohols are alcohols in which the carbon atom carrying the OH. So if we look to this image down here, these are all primary alcohols because the carbon atom that is carrying the OH is only bonded to one other carbon. So if we look here, right, the carbon atom over here that is carrying the OH is only bonded to one other carbon. Same with ethanol, methanol, and propanol. Secondary alcohols are alcohols in which the carbon atom carrying the OH group is attached to two other carbons. So we can't see it here, but if this carbon atom over here was attached to another carbon somewhere else, it would be a secondary alcohol. And tertiary alcohols are alcohols in which the carbon atom carrying the OH group is attached to three other carbons. So in terms of the questions that you might get in school, it's a good thing to know what primary, secondary, tertiary alcohols are and know them in the sense of being able to define them and maybe draw them out as well, because it is a possible question that can come up. So now let's go at naming this, right? So let's go through this. So let's look at the longest carbon chain. So the longest carbon chain here. Oh, let's first look at the functional group. So the functional group here is I'm looking, and I see the presence of OH bonded to carbon, right? So this is how they would normally lay it out. Obviously, if we're expanding it out, the oxygen is bonded to the carbon and the hydrogen is bonded to the oxygen, right? It's not like the carbon is bonded to both oxygen and hydrogen. So we see the OH group, the hydroxyl functional group, and we realize that this compound is now an alcohol. So we know it ends in like ol, so we know the compound ends in ol. Now we just need to find out what the longest carbon chain is. So if we're trying to find out what the longest carbon chain is, let's look through it now. So 1, 2, 3, 4. So if we look over here, the longest carbon chain is 4 now. So we have the longest carbon chain 4, and so the prefix is but. So the prefix is but. So we know it's a type of butanol, right? It's a type of alcohol with 4 carbon chains in it. It's a type of butanol. But we need to now, because you can see here now that the functional group here can move around, right? It can move around to any of these hydrogens, can be replaced with OH, right? So we need to specify, we need to know between the different types of butanol. So we have butan 1-ol, butan 2-ol. We need to know between the different types, right? So let's count. So this hydroxyl functional group is on the first, the second. So it's in the second carbon. So it's attached to the second carbon. And because it's attached to the second carbon, we name it butan 2-ol. Yep, so let's go through this now. So the longest chain is 4 carbons, so we get but. The functional group is a hydroxyl functional group. Prefix is ol. The position of the functional group is on the second carbon, and so the name becomes butan 2-ol. So now if we count from right to left, we get the third carbon, right? But the third carbon, it can't be the third carbon, right? Because there's a line of symmetry across this line. So we can flip the compound around, and this third carbon now becomes the second carbon, right? If we flip it around. So at max, you can only have butan 2-ol. So there's only two variations of butanol, butan 1-ol and butan 2-ol, because butan 3-ol is just butan 2-ol flipped around, and butan 4-ol is just butan 1-ol flipped around. So if that doesn't make sense, have a go at writing out butan 4-ol and butan 3-ol, and then compare it to butan 2-ol and butan 1-ol. I guarantee you it's just the same compound but flipped around. So that's alcohols. Now we'll go on to side branching. So you might have heard me say earlier when we're trying to find the parent chain, we're trying to find the longest unbranched carbon chain. So branching can also occur in organic compounds. So what we call a branched thing is an alkyl group, so it's an alkane missing one hydrogen. So we have methyl and ethyl groups. So if we look over here, we have methane, we remove one hydrogen and it becomes methyl. We have ethane, we remove one hydrogen and it becomes ethyl. And what happens is these methyl and ethyl groups, they end up bonding to the parent chain. So if this methyl, so let's take two methyl groups. So let's take butane, right? So we have butane over here. And let's take two methyl groups. If we take two methyl groups and bond it to this butane, so we bond it here and here, we get 2,3-dimethylbutane. So let's read the thing now. In the same way that hydrogens can be substituted by halogens, they can also be substituted by methyl and ethyl groups. Same with propyl groups. It can keep going. So they're also listed in alphabetical order. And so if there are also halogens, then everything is listed in alphabetical order. So basically, right, we also have a prefix before the methyl and ethyl groups. So if we look at this compound right here, 2,3-dimethylbutane. Yeah, so let's look at 2,3-dimethylbutane over here. So firstly, so this compound looks pretty terrifying. It's like a jumble of carbons and everything, but we need to take a look at to analyze everything that's going on here, right? First thing that we do, functional group. So we look over here, all single bonds, it's going to be an alkane. So we know the functional group is an alkane now. Now we need to find the longest carbon chain. So if we look here, follow my cursor now, we have 1, 2, 3, 4. So that's 4. Now we have 1, 2, 3, 4. That's 4. We have 1, 2, 3, 4. That's 4. 1, 2, 3, 4. That's also 4. And we have 1, 2, 3. So that's not 4. So the longest carbon chain is 4. And there's like many different ways that we can achieve the longest carbon chain of 4. What I want you guys to realize is that it doesn't matter how you get to the longest carbon chain of 4, any one of those will work. So for this example, I didn't take a straight line chain of 4, I took the zigzag pattern, like the Harry Potter lightning bolt type pattern. So I got 1, 2, 3, 4, C1, C2, C3, C4. I labeled them over here. So now if we look at this diagram, right, we have the first, so we have two methyl groups. So this is our longest carbon chain. So we know it's a type of butane, right? We know it's a type of butane because it's an alkane. So if we go through this 4 over here, we have C1, C2, C3, C4. Now we need to look at where the side branches are bonded together. So this first methyl side branch is bonded to C2, the second carbon. This third methyl functional group, or this third methyl group, is bonded to the third carbon, C3, the third carbon. So two methyl chains. So because it has two methyl chains, it becomes dimethyl. So this di is very important. You need a prefix. It can become trimethyl, dimethyl. You need a prefix. If it's just one, it's just methyl. So there's no monomethyl. It's di, tri, and then it keeps going upwards. So because there's two methyl groups over here, we get 2,3-dimethyl butane. So the dash is after the numbers, and we get 2,3-dimethyl butane. So this 2, 3 denotes where the methyl groups are bonded to the main carbon chain. And another thing that's very important is over here it says the same way that hydrogens can be substituted by halogens, they can also be substituted by methyl and ethyl groups, and these substituted groups are listed in alphabetical order. That's ignoring this like prefix of di. So if we have an ethyl group bonded to it, it will become ethyl methyl butane, right? Not methyl ethyl butane, it will become ethyl methyl butane because E comes before M. So even if we have ethyl dimethyl butane, even if we have a dimethyl and ethyl group, and D is like before E, it would still be ethyl dimethyl butane because we forget about the prefix, we're only looking at the actual like alkyl group. So we forget about the prefix when we order it in alphabetical order. So now let's go into aldehydes and ketones. So the functional group here is a carbonyl functional group. So the CO double bond. So this carbonyl is double bonded to an oxygen and single bonded to two other things. So in aldehydes, the carbonyl is bonded to one hydrogen and one further chemical group, i.e. the carbonyl group is always on the end for an aldehyde. So we have the chain of carbons, and then at the end of the chain of carbons, we have a carbonyl group. And if it's at the end, we know it's an aldehyde. So naming aldehydes, because they're always at the end, so the suffix is al for this one. So because the functional group is always at the end, we don't need to specify the number of like where the locant number or where the functional group is on the carbon chain, because it's always attached to carbon number 1. So that's very important. Remember, it's always attached to carbon number 1, not the last carbon, but the first carbon. So now let's look at ketones. So for ketones, they're very similar to aldehydes, except the carbonyl functional group can be anywhere, just not at the ends, because if it was at the ends, it'd become an aldehyde. So anywhere but the ends, the carbonyl functional group can be, and when that happens, we name it a ketone. So let's look at the suffix, right? The suffix for this one is -one. And so so let's look at the diagrams over here. The smallest ketones possible is propanone. And propanone is the smallest one because if we have ethanone, there is no ethanone because the carbonyl groups can only be at the ends. And if it's at the ends, then it becomes an aldehyde, so it becomes ethanal. So if we look at the aldehydes, we have methanal, ethanal, propanal. And if we look at the ketones, we have propanone and 2-pentanone. So propanone, we don't have to specify, but for butanone and pentanone, we need to specify on what carbon the double bond or the carbonyl functional group is bonded to. So let's take a look at this, right? So let's look at this first of all. So we need to look at the functional group here, right? Let's look at the functional group here, right? So looking at the functional group here, we need to take a look at where the double bond is. So the double bond is present in let's take a look at the functional group first. So we see a CO double bond. So looking at the CO double bond, what we first notice is that the CO, the carbonyl functional group. So with the carbonyl functional group, we know that it's either an aldehyde or a ketone. So to differentiate between the two of them, we need to look at the location of the carbonyl functional group. So the carbonyl functional group is located at the very end. So it's located at the very end of the 5-carbon chain. And because it's located at the very end, we call it an aldehyde, right? Because for a ketone, so the carbonyl group is always on the end for an aldehyde. So if we look over here, the carbonyl group is on the end of the chain, and so it's an aldehyde. If it's a ketone, the carbonyl group will be on one of these three positions where the hydrogens are, but it's on the end, so it's an aldehyde. So now we know it ends in al. Now we need to look at the longest chain. So the longest chain is 1, 2, 3, 4, 5. 5 carbons. What is the prefix for 5? It's pent. So we have pentanal. So yeah, longest chain is 5 carbons, so we know the prefix is pent. Functional group is an aldehyde because the carbonyl functional group is at the very end. Are there any side branches? No. So this is something that you need to check now. Because we've now covered side branches, always check to see if there are side branches on the compound. Here we can see it's a straight chain compound, so there's no side branches. And so the presence of side branches, no. Now we look at the name. So the name is pentanal. So we have the pent and we have the al, we just put together pentanal. Now we get to carboxylic acids, my favorite organic compound. So the functional group is a carboxyl functional group. So we have the carbonyl and now we have the carboxyl functional group. So it's given by COOH. So you might have seen this before on acetic acid, CH3COOH. So yeah, so over here, so a cool little fact, CH3COOH is a carboxylic acid. Its IUPAC name is ethanoic acid. So you can see from here, right, we have CH3COH. So we can say that this organic compound is 2 carbons, one here and one here. So the drawn out form of this is like this. So it has 2 carbons, right? So the longest chain is going to be 2. What is the prefix for 2? Eth, right? Eth. And if we go back over here to the suffix in the pink box, the suffix is oic acid. So we just put them together and we get ethanoic acid. So this acetic acid, another name for this in IUPAC naming, is ethanoic acid. And because the functional group is COOH, yeah, it can't move around, right? Because the carbon double bonded to an oxygen and single bonded to a hydroxyl group, it's always at the end. It can't be anywhere else. It always has to be at the end of the parent chain. So because of that, we don't need a locant number. We don't need to label which carbon the functional group is on because it'll always be at the end, just like an aldehyde. So another side note is that when numbering the carbons, the one with the carboxyl group is always carbon number 1. So we always need to start the chain from the one with the carboxyl function group. So looking at this picture over here, let's name these, right? So we have C double bonded to O with an OH on the side. So it's like a carbonyl and the hydroxyl bonded together, so carboxyl. And let's look at the number of carbons here, 1 carbon, so it's methanoic acid. Let's look over here. So C double bond COOH, CH3, ethanoic acid. So two C's, and we have the carboxyl function group, ethanoic acid. Let's look over here now. Number of C's present, 1, 2, 3, 4. 4 C's with a C double bond O with an OH bond on here. So we get butanoic acid. And then the final one is 1, 2, 3, 4, 5, 6. 6 over here, hexanoic acid. It's very simple. So let's try and name this now. So this convention might be a little bit tricky because now we're being introduced into different ways of showing us the compound. So we don't need to worry too much about this. But yeah, basically this has 1 carbon, this has 1 carbon. So all the points have 1 carbon on it. So if we're counting the points or the vertices, we have. So let's look at the longest chain now. So we know the functional group is COOH. So we know it's a carboxyl function group. So it's going to end in oic acid. So let's look at the longest chain. Now we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We have 5 here. So 5. So it's going to be some form of pentanoic acid with side branching present, right? Because you can see how it branches into 2 things, and one of this forms the parent chain, so the other one is a side branch. So there's going to be 1 side branch present. So it's some form of pentanoic acid. So now let's count. So we have 1, 2, 3, 4, 5. So 1, 2, 3, 4. So it's going to be on the 4th one. So it's going to be 4-methyl pentanoic acid. So 4-methyl pentanoic acid. The answer for this. So if we look here, so this is the first one because if we go back, right, the carboxyl group is always on carbon number 1. So if we're naming this dot over here is going to be carbon number one. So carbon number one, 1, 2, 3, 4, 5. So 1, 2, 3, 4. On the fourth carbon, we have another side branch. So it's going to be 4-methyl pentanoic acid, 4-methyl pentanoic acid. So going to what I was talking about before, the different methods of showing of like notate or like showing us a different compound. We have skeletal, condensed structural, and structural. So taking a guess at what these are, condensed structural and structural. So obviously one is going to be the condensed version of another. So this is condensed structural and this is structural formula. So most of the time in school, or all of the time in school, you're going to be writing in structural formula. And what's very important is you always write the H's. So always draw out every single H whenever you write a structural formula, because you're prone to losing at least 1 mark if you miss out an H or if you like draw an incomplete compound. So make sure you always fill out your hydrogens, which are the most tedious part of drawing in structural formula. Next one is skeletal. So as I mentioned before, the points or the vertices form like the carbon. So we have this dot over here is going to be CH3. This dot over here is going to be CH2. This dot over here is going to be CH3. So same here, CH3 corresponds to this point over here. CH2 corresponds to this point over here. And then CH3 corresponds to this point over here. Same over here, CH3, CH2, CH3. So it's the same compound, but represented in different ways. So now let's go on to amines. So for a primary amine, the functional group is NH2. So we have so the amino functional group, and the suffix is amine, right? So we have primary, secondary, and tertiary amines. So basically, nitrogen is capable of bonding to 3 things instead of oxygen, which is capable of bonding to 2 things. So when we have an organic molecule, stuff can start joining on the other side. So the syllabus doesn't really mention secondary or tertiary amines, so it doesn't really, so don't panic if it doesn't make sense. But for the sake of explaining, primary amines, so the nitrogen is only bonded to one organic group. So if we look here, so it's very similar to alcohol. So the primary amine is where the carbon holding the nitrogen is only bonded to one organic group. The secondary amine, the nitrogen bonded to 2 organic groups, and the tertiary amine, the nitrogen bonded to 3 organic groups. So the nitrogen can be bonded to 1 organic groups like this. So there's a primary amine. The nitrogen can also be bonded to 2 organic groups. So like another carbon over here. And then the nitrogen can also be bonded to 3 organic groups or another carbon over here. So yeah, primary, secondary, tertiary amines. Doesn't probably make sense right now, but you might come across it later. So that's amines, very simple. Now we have amides. So amides is very similar to the layout of a carboxylic acid. So we have the C double bonded to O, and we also have the NH2 attached to it. So it's a carbonyl bonded to a nitrogen. So we have the amide functional group. So the suffix for this is amide. So if we go back here, the suffix for an amine is amide. So we have propan 1-amine, butan 1-amine, pentan 1-amine because it's bonded to the first carbon. Methanamine, ethanamine, octan 1-amine because it's bonded to the first carbon again, etc. So that's how we name it. Because NH2 could be anywhere, just like an alcohol, we need to label where on which carbon it is in. For an amide, though, just like a carboxylic acid, it's only on the first carbon. So if we see a carbon with a nitrogen attached to it, but the carbon is also double bonded to an oxygen, it is an amide. So it's always on the first carbon as well. So, side note again, amide groups can only be on the end of the parent chain. Anything added onto the other side of the end is actually not touching the parent chain. This means that when numbering, things come off of the N are given an N locant number. So basically what that means is, right? So we have NN unsubstituted amide. So this will be methanamide. So if we look over here, we have methanamide. So assume the R is an H. We have IUPAC name for this is methanamide. So to say now that we substituted this like H with a CH3 group, so a methyl group, right? So now we would have N-methyl methanamide, right? Because instead of this CH3 is bonded to the N, so we have N-methyl methanamide. So instead of saying 3-methyl methanamide or a number, we have N-methyl methanamide. And now if we look at this example, because we have 2 methyl groups bonded to it now, we have N dimethyl methanamide. So that's how we would go through it. So di is the prefix because there's 2 of the methyl groups, and that's how we would run through it. So now we're nearing the end of our IUPAC nomenclature, or our naming of through IUPAC means. So now let's go through what happens when a halogen is, or like a hydrogen is substituted by a halogen. So we get things like chloroethane, we get like chloroalkanes, bromoalkanes, etc. So yeah, let's look at this one, right? This one is called a chloroalkane or chloroethane. So this is called a chloroethane because, and there's no number. So you can see here we have two bromobutane, we have numbers. So this one, we don't really need a number because if we look here, right, there's only one possible, no matter which chlorine it's going to be bonded to, it's still going to be chloroethane, right? There's no 1 and 2 chloroethane. So it's going to be the same because you can flip it over and it's going to be symmetrical. So we can look at 2-bromobutane. So just like before, it's just like we have a functional group over here. So this is a halogenated organic compound. So just like that, we need to label on which carbon the bromine is bonded to, because it could be 1-bromobutane or 2-bromobutane. So we need to specify. So this one is 2-bromobutane because it's bonded to the 1, 2, second carbon. So now we also have dichloromethane. So we have the prefix as well. So we have dichloromethane because there's the presence of two chlorines. And we don't have a number here because there's only one carbon. So there's only one possible carbon it could be bonded to. So let's look at the question over here. Why isn't 1,3-dichlorobutane labeled 2,4-dichlorobutane? So if we look over here, right, if we number it from left to right, we get 1, 2, 3, 4. So we get 1, 3, dichlorobutane. But if we number from right to left, we get 2,4-dichlorobutane. So it's not 1,3-dichlorobutane because if we flip around 2,4-dichlorobutane, we get 1,3-dichlorobutane. And we're always like aiming to display it with the lowest possible combination of numbers. So the numbers that add or multiply to give the lowest possible combination, we're just trying to like achieve the lowest possible numbers possible. And so it will be 1,3-dichlorobutane instead of 2,4-dichlorobutane. Over here, we can't really change much. We could do 3,3-dichlorobutane, but obviously 3,3-dichlorobutane is just 2,2-dichlorobutane flipped around. So yeah, it's just going to be 2,2-dichlorobutane. And we can also add a lot more halogens than just butane. We can add fluorine, chlorine, and iodine. So this becomes fluoro, chloro, iodo. So a little bit more about halogenated organic compounds. Where there are different halogens, name them in alphabetical order. Just like the previous where we said where there's different alkyl groups, we name them in alphabetical order. So ethyl before methyl, even though there's more carbons in the ethyl group. So if we look over here, right, we have 4-bromo, 1-fluoropentane. So note, if you number from the right, then the first halogen is on carbon 1. Whereas if you number from the left, then the first halogen is on carbon 2. Thus, you should number from the right. So what they're trying to say is you'll get a lower number overall if we number from the right going left, as opposed to if we number from the left going right. So what if numbering from either end is the same? So we get 2, 2, so they're both the same, right? So we get 2, 4, so so no matter where we label it from, we'll get 2, 4 as our numbers, right? And so we can either get 2-bromo, 4-fluoropentane, or we could get 4-bromo, 2-fluoropentane. So which one is correct? So it could be 4-2, it could be 2-4, we're not sure. So the answer to this question is we use the name with the smallest locant number first. So it's not 4-bromo, 2-fluoropentane because bromo comes first, so we give bromo the lowest number. We give bromo the privilege of the lowest number. So it becomes 2-bromo, 4-fluoropentane. But that is only when it's similar, when we're numbering from the same. So this is where IUPAC can get quite a little bit complicated because of all these niche rules that it has. So when numbering from either side is the same, we give the smallest locant different halogens, right? So going back over here, we can name them in alphabetical order: 4-bromo, 1-fluoropentane. That's all good. Moving on. So now, naming organic compounds. So the process for naming organic compounds. So this is like a summary of what I've gone through. So we have gone through this in the previous question. So we look here, right? We go through this process where we go through the longest chain, functional group, side branches, name. It's just that thought process simplified down again. So firstly, we count the number of carbons in the longest unbranched carbon chain to identify the stem name. So stem name is like basically what we use to identify the prefix. So whether it's pent, eth, meth, etc. And then we add the suffix, right? So we identify the functional group, and then we identify what the suffix will be. So what will it be? An ane, an ene, an oic acid, an ol. So yeah, we identify what it will be. And then we add the halogen and then we'll add it together, or if it's different, we have the halogen prefixes. So we need to make sure that the halogen prefixes are listed in alphabetical order, and also the alkyl groups, so methyl, ethyl, propyl. So those side branches, we need to make sure they're also listed in alphabetical order. And now let's read the notes over here. So the locant number, which is what I have been referring to occasionally, tells you which number the halogen is attached to. So I have mentioned this differently. So I mentioned which carbon is the side branch bonded to, or the functional group bonded to, right? That's basically the locant number. And then every single halogen needs its own locant number, even copies the same halogen. That's why we get something called 2,2-dichlorobutane. It's not just 2-dichlorobutane, it's 2,2, because each chlorine atom gets its own locant number. And then we also get di-tri-tetra prefixes for the halogens, and also for other functional groups as well, and also for the side branches as well. And then, as I mentioned before, these di-tri-tetra prefixes are not considered in alphabetical order. So the alphabetical order only refers to like the actual word. So methyl, ethyl, it only applies to those, and the fluoro, chloro, bromo, iodo. It doesn't apply to the di, tetra, and tri. So now, final question to identify like what the compound is. So let's go through the thought process again. So the first thing that we do is we try to identify what is the functional group here. So the functional group, I can only see, so this is what we would call like a mix of condensed structural formula and also structural formula itself. So, you know, the CH3 would just be a carbon bonded to 3 hydrogens. So looking at this, I can tell instantly that it's a saturated hydrocarbon, so it will be an alkane. Looking at these answers, they're all alkanes, they all end in ane, so that's not going to rule out any options. So now what we need to do is we need to find the longest carbon chain. So going through this, we have 1, 2, 3, 4, 5, 6. So that's 6, pretty long. Let's go through here. 1, 2, 3, 4, 5, 6, 7. So 7. So now we know that the longest carbon chain is 7. So it's going to be a form of heptane. So automatically, C and D, they're ruled out. So heptane is our answer. So it's going to be either A or B. So now we just need to identify like where it's going to be located. So obviously, as I mentioned before, we go for the answer with the lowest possible like numbers, outcomes, right? So we have two options, 355, 335. So let's do this. Let's count from left to right. So we count from left to right, we get 3, 5, 5. So the left to right is option B. Right to left is 3, 3, 5. So right to left is A. So we would pick A because 335 has a lower like overall locant number than 355. So we were aiming to go for the lowest number. And obviously because there's 3 side branches, it becomes trimethylheptane. So the answer is A, 335 trimethylheptane. So now, finally, esters. So when drawing esters, we draw the alkanoic acid. So esters are also another form of organic compound. It looks something like this. So C double bonded to O, single bonded to O with another like carbonyl or like a carbon chain attached to it. So when drawing this, we have the alkanoic acid or the carboxylic acid on the left, and the alkanol or the alcohol on the right. And so the carboxylic acid on the left, the alcohol on the right. And the carboxylic acid is the one that has the oxygen double bonded to it. So this is kind of what an esterification reaction looks like. So this is very probably quite good to remember. So obviously the length of these carbon chains can be changed, and accordingly the name of the ester will change, and also the length of the ester will change. So we have alkanoic acid plus alcohol goes into alkyl alkanoate plus water. So if we're reacting butanol, it becomes butyl propanoate. If we're reacting methanoic acid and ethanol, we get ethyl methanoate, etc. So that's how the naming convention works. It's very similar to this image over here, and we can use that to kind of derive what the names for other esters will be. So now, a summary. So we have the carboxylic acids, the amides, the aldehydes, the ketones, the alcohols, and the amines. So we have the carboxyl, the amido, the oxo, the hydroxy, the amino. We have the oic acid, the amides, the al, the one, the ol, the amines. And then we also have the structure of the functional group. So we have the C double bonded to O with an OH group attached to it. We have the C double bonded to O with an NH2 bond attached to it. We have the C double bonded to O with just an H attached to it. Obviously, this is the aldehyde. We have the C double bonded to O in the middle of two carbon chains. So this R over here is basically, it's a symbol that represents another carbon chain. So R dash means a carbon chain different to R. So it's two different carbon chains. That indicates that this carbon is in the middle of this two different carbon chains. And so the ketone is going to be in the middle of the carbon chain. So yeah, it indicates that it's not at the end. But over here, for the aldehyde, because the R is only on one side and the other carbon is bonded to the H, we know that this C finishes off this carbon chain R. So the C double bond to O is at the end of the carbon chain, and so it becomes an aldehyde. Now alcohols, ROH, so obviously the hydroxyl group is bonded to the carbox, or the carbon chain. And then for an amine, we have the NH2 with the R. So the NH2 is attached to a carbon chain. So now the hardest part, what if there are multiple functional groups, right? So they don't just have to give us an alkane or just an alkene. They could give us multiple functional groups. So for that, what you need to do is you need to keep in mind this hierarchy: alkanoic acids, amides, aldehydes, ketones, alcohols, amines, alkynes, alkenes, and then alkanes. So this is the hierarchy that you need to keep in mind. So what we do for that is we identify the parent chain. So we need to count the number of carbons in the longest unbranched chain. And then if there are multiple options of the same length, we use the one that results in the shortest branches. So we identify the parent chain. And then we identify the parent functional group. We identify the parent functional group by looking at the hierarchy. So if we have an alkanoic acid and an aldehyde present, the parent functional group is going to be the alkanoic acid. So yeah, whichever one has the highest precedence or closer to rank 1, looking at the hierarchy on the right. And we use this for the suffix. And then what we do is we identify all the substituents. So these will be all prefixes. And then we list them in alphabetical order. And then we add the double and triple bonds if there are any. And then we add the di, tri, tetra prefixes if there are any. And then we number the carbon chain, and then we add the locant numbers to prefixes. So it's a very methodical process, and this is the kind of steps that you follow. But the very important thing to take away from this slide is to know this hierarchy over here. So alkanoic acids, amides, aldehydes, ketones, alcohols, amines, alkynes, and alkanes. Right, let's go into multiple functional groups now. So these are a couple examples of multiple functional groups. So we have 5-chloro-2-pentene. So we have the halogenated functional group, and we also have ene. So let's look at this, right? So it has 5. So we labeled this 5 because we let the functional group take precedence. So the functional group, we count from left to right because we want the functional group to have the lowest number. And so because of that, we also count left to right when labeling chloro. So we could count right to left for chloro and left to right for pentene, but that's just not how we do it for IUPAC naming. So we always have to stick to one letter of means of counting, or one direction of counting. And what takes precedence is this number over here, the number of the functional group. So we count from left to right to give the functional group the lowest number. So counting from left to right, the double bond is in the second bond slot, so it's 2-pentene or pentuene. Counting from left to right, the chlorine is on the 5th carbon, so it becomes 5-chloro-2-pentene, or 5-chloropentene. Now let's look at the second option over here. So again, if we look back, so we have a ketone and we have an alcohol. So if you go back to the hierarchy now, ketones are above alcohols. So because of that, because ketones are above alcohols, ketones will take precedence. So what we do now is we try to make the ketone have the lowest possible locant number. So we count from left to right again. So the ketone is bonded to the second carbon, so it becomes 2-pentanone or pentan-2-one. And then we count for the hydroxyl functional group. So we have 1, 2, 3, 4. So the hydroxyl functional group is bonded to the 4th carbon, so it becomes 4-hydroxy-2-pentanone. Same goes for this example, and this example. It follows the same way. We choose whichever functional group takes precedence, and then we let that one have the lowest locant number. So yeah, each of 2 or more compounds with the same formula but are different. So this, what we're going to be learning now, is called isomers. So there are 3 types of isomers: chain isomers, position isomers, and functional isomers. So a definition is each of 2 or more compounds with the same formula but a different arrangement of atoms in the molecule and different properties. It's probably a definition you might want to take down. And then we're going to be learning structural isomers. So there's 3 types of these structural isomers, which are chain, position, and functional. So Like the name might suggest, and the names are very indicative of what these do, the chain isomers are where the skeleton, or like the carbon skeleton, so the carbon chain is reordered to create a different structure. So pentane has 3 different isomers. So one is where this end carbon is now like moved over, so moved one over as a side branch. And then the other one is where a second carbon is moved to form 2 side branches. So yeah, 3 different ways where the carbon chain, so the chain is what's being disrupted. Next one is position isomers. This is where the functional group changes position. So pentan 1-ol becomes pentan 2-ol, right? So that would be a position isomer. So pentan 2-ol is a position isomer of pentan 1-ol. Yeah, so pentanol has 3 position isomers. We have pentan 1-ol, pentan 2-ol, and pentan 3-ol. So these are the 3 position isomers of pentanol. And position isomers vary based on the location of specific functional groups, as I mentioned before. So chain isomers are where the chain varies. Position isomers are where the position of the functional group varies. And now, so for this question, try drawing all the position isomers of dichloropropane. So obviously we have the functional group here is the halogenic functional group. So we have the chloro, and the chloro can be in many different places, right? So if we're now looking at dichloropropane, which is what this question was asking, we have 1,1-dichloropropane, 1,2-dichloropropane, 1,3-dichloropropane, 2,2,2-dichloropropane. All right, so now we have functional group isomers. So going back to before, chain isomers are where the carbon chain is being disrupted. Position isomers are where the position of the functional group is being disrupted, and functional group isomers are where the functional group itself is changing. So if we have over here cyclohexane and 1-hexane. So cyclohexane is basically an alkane, but like in a circle, and it has a different functional group. So cyclohexane is a functional group isomer of 1-hexene. Even though they have the same like molecular formula of C6H12, they have different functional groups. So that's how it works. Yeah, so in summary, functional group isomers vary based on changes to functional groups, and this will result in the most drastic change in their physical properties because like the functional group is what drives its properties and it's being physically changed. And that was the crux of naming organic compounds. That was basically most, if not all of it. We did go into pretty good detail with that one. So I hope you guys know how to label or name organic compounds now. Now we will go into the safety and economics aspect of Module 7. So this slide is going to be on the handling and disposal aspects of chemicals. So you need to be able to know like the safety data sheet, the SDS sheet. Also, you need to be able to know how to handle stuff. So storage, you need to be able to carefully label the containers and store like toxic substances the correct way. So if you're handling stuff that could like vaporize, you need to be able to know to like put them in like a fume cupboard when doing them so that the vapor doesn't go into your nose, so the vapor isn't inhaled by people. You also need to be able to know to use protective equipment, the effective protective equipment, and also especially when you're doing experiments, use it like have it well ventilated unless obviously it requires like it to be not well ventilated. But most of the time in school you'll require it to be well ventilated. So your teachers might open the door or like the window quite often, and also don't sniff your like chemicals, especially if there's gas coming out of them. And in terms of disposal, this is also very important. You always need to make sure that unless it's very mild, you know that you can pour them down the sink. Obviously, ask your teacher. If it's chemicals like chlorine, so if it's like salts, if it's like so in chemistry you'll go through testing different types of salts for testing the solubility and stuff. So, and you're also doing titration with different types of salts and acids especially. So make sure to not pour them down the sink. Your school will have like waste containers, or their lab should have waste containers provided for them to dispose of them properly. And this applies to liquid and solid organic waste as well, and they should be treated separately. So liquid organic waste should be treated separately to solid organic waste, as they're disposed of separately. So they need to be put away in different positions. So now we can go on to one of my favorite parts of Module 7, which is the implications of hydrocarbon use. So we have environmental, economic, and sociocultural implications. So without even looking at these slides, hydrocarbons, fossil fuels, right? What are some economic implications? So fossil fuels, extracting them, the entire world relies on them, right? So if a country can gain access to fossil fuels from their country, like from the the minerals in their country, what happens is they become very rich. So in the short term, they'll experience an economic boom and economic prosperity. That's one economic result of or one economic implication of hydrocarbon use. But so that's a short-term advantage, but it also has a long-term disadvantage. So because the country now is like, riding the high from the hydrocarbon, like selling hydrocarbons, right? They're going to become overly reliant on hydrocarbons. And the main like thing about hydrocarbons, or the main factor, is that they're non-renewable, right? So an over-reliance on fossil fuels can stifle economic growth, or maybe even crash the economy, because an over-reliance on them will then cause the economy to like not have any means of sustaining itself without hydrocarbons, and hydrocarbons will eventually run out. So it's an unsustainable model in the long term. So it's a long-term disadvantage, but a short-term advantage. And there's also some environmental implications. So extracting these fossils, there are large mines, large open cut mines as well. So it does lead to increases in deforestation, increases in land clearing, and which is also loss of natural environments, loss of wildlife. And there's also the aspect of combusting fossil fuels that releases greenhouse gases, contributes to the greenhouse effect, and also climate change. And it also, if we're thinking about like the direct implications, we're like, adding like effluents into the air, like sulfur and stuff, and that causes acidic rain. And this can also affect the ecosystems, disrupt ecosystems. In terms of like socio-cultural implications, there's like positives and negatives. So mining has, obviously in Australia itself, has devastated the Aboriginal and Torres Strait Islander communities, because they've invaded their land and they've taken up their land in terms of and used them for mining. So the sale of land to mining corporations and subsequent mining activity extinguishes access to native title and their ownership of land. But there's also a positive in that aspect, where you could say that it also creates a lot of jobs for many people. Like this opening of new mines and new factories can create a lot of jobs for people. So there's always advantages and disadvantages to everything. Yeah. Oh, there's also, for social cultural implications, there have been wars that have been generated on the use of hydrocarbons. So, our over-reliance on it has led to like aggression between countries, for example. So if a mine is found in a border, for example, between two countries, who owns that mine, right? So there have been border disputes over who has access to these resources, etc. So it has led to wars, and maybe maybe not wars, but like, international fights and sanctions. So, but essentially, these implications of hydrocarbon use, you'll go through it in more detail in school, but in terms of what will come up in your exams, these questions often come up as long response answers. So probably like 5 markers to like detail the economic implications of hydrocarbon use, etc. Or they could come as a part of a long response question, where like you're talking about how to synthesize hydrocarbons, and then in the next part, in part B of the question, they ask you, what are some of the environmental implications of this? So yeah, keep in mind those are the types of questions that you might get. So you need to be prepared to write a lot about this stuff. So this is also one of my favorite parts, comparing fossil fuels with biofuels. So biofuels are like organically generated fuels. So it's generated from organic compounds. So a couple advantages and disadvantages. I basically just listed one of them. So the first advantage of biofuels is that it's renewable. So because it's renewable, it's created by the fermentation of cellulose from crops. And so we don't need to worry about a long-term disadvantage, because we can just keep making it, assuming that we have the technological ability to keep producing at a rate that we can, use it if like comfortably. It can also combust completely and lead to less pollution. So biofuels are partially oxidized, which means they have some oxygens in them, so they have oxygen molecules in them, so it's easier for it to combust. So we need to provide less oxygen for it to combust, because the biofuels already have oxygen inside of them. Fossil fuels don't have that, because they're just hydrocarbons, right? So we need more carbons for them to combust. So biofuels combust more cleanly, fossil fuels don't. So now let's look at advantages of fossil fuels, right? So fossil fuels have like a much larger energy output, so we can get a lot more like energy out of fossil fuels than biofuels right now, like ethanol, for example, which is a biofuel. That is one advantage. Some disadvantages of fossil fuels are, as I said before, they're non-renewable and so unsustainable. And the thing is, as it becomes more and more unsustainable, the prices will rise and rise. So that does pose an economic disadvantage in that sense as well, in terms of availability and cost. And yeah, and like more fossil fuels, they also combust uncleanly, or like fossil fuels also tend to partially combust, and so they'll release more like toxic carbon monoxide and soot into the air. In terms of biofuels as well, some disadvantages are you need a large amount of land to cultivate the crops required for biofuels. So there'll also be a lot of land clearing and replantation. So there'll be a loss of diversity in terms of plant life. There's also like the produce that you get from biofuels, they stink a lot. So there's a lot of odorous fermentation and waste products. So you also need to be able to like dispose of that effectively so that it doesn't like stink up like thousands of acres. Another disadvantage is it has a lower heat of combustion. So this means it's going to be less effective in colder climates. So things like, in like the northern hemisphere, or like the poles, basically. The closer you get to the poles, the colder the climate is, it's going to be less and less effective. And then also, because it's like it's hygroscopic, so it absorbs moisture from the air. That's what hygroscopic means. So biofuels, they absorb moisture from the air, and obviously, like, moisture, water with an engine doesn't really go well. So because they absorb moisture from the air, the engines require modification for them to be used. So currently, we can only use around 15% in our like car engines. So if we need to use them effectively and comfortably, we need to spend a lot of money on inventing engines and making engines usable or like accessible, and making these engines that can use biofuels more accessible. So similarity. So the sources of energy are quite similar, and they're both suitable for combustion engines, obviously with varying success rates. They're both organic molecules, and they share the same carbon backbone. Differences: their size is different. The heat of combustion is very different. Fossil fuels have a much larger heat of combustion. One is renewable, one is non-renewable, one is complete, one is incomplete combustion, and the production process is also very different. So fossil fuels are formed over millions of years, whereas biofuels take a fraction of the time to make in like respective millions of years. So now we'll go on to properties of hydrocarbons. So this is mainly in relation to boiling point. So hydrogen bonding, so there's a couple of different things, right? So in class already, you'll have learned about, dispersion forces, dipole forces, polar forces such as dipole forces, and hydrogen bonding. In terms of boiling points, so the questions that they can ask in terms of the properties are, which one can have a higher boiling point, basically. So will an alcohol have a higher boiling point than an amine, for example? And you need to be able to identify which will have a higher boiling point. And if we're thinking about boiling point, we need to say, like, defining boiling point, right? Boiling point as a definition is basically the amount of energy required to overcome the bonds between the molecules, right? So the bonds between individual molecules, if we overcome that, we reach as boiling point. So hydrogen bonding between molecules is quite high in alcohols because it's got the polar OH bond. So the H is like the donor and O is like the acceptor. So this means that the melting point and boiling point are higher than their corresponding alkanes, and they're also higher than corresponding alkanes of similar molar mass. So molar mass also plays quite a big quite a big aspect on the boiling point, especially when we get to really large compounds like alcohols, because they're hydrogen bonding, they'll obviously have a higher boiling point than methanol, or let's say propanol. Propanol will have a higher boiling point than propane, but propanol will not have a higher boiling point than maybe an alkane with like 50 carbons in the chain. This is because of the effect of dispersion forces. So alkanes are nonpolar, they don't have any polarity in them, so they can only react through nonpolar dispersion forces. So even though they react through very weak dispersion forces, the strength of these dispersion forces can be large enough to overcome like the hydrogen bonding. So this is how it happens, right? So we think of the molar mass, right? So when there's a massive amount of carbon chain, right, there's also going to be a lot of electrons within that compound, right? So if there's 50 carbons in the alkane chain, there's going to be a lot of electrons, right? And so these electrons are moving around, and the temporary imbalances in charges caused by these, like the electrons, are much greater if the compound has 50 carbons compared to 10 carbons, right? Because the compound with 50 carbons will have a greater electron density than the compound with 10 carbons. And so the imbalance in charge will be a lot greater. And because of this, the strength of the temporary dipoles that are formed are also a lot greater. And if the strength of the temporary dipoles are formed are greater, then the strength of the dispersion forces are also greater. So what happens is the greater the molar mass, or the greater the greater the chain length of a compound, the greater its boiling point is. That's why I mentioned alcohols have a higher boiling point than alkanes of similar molar mass. So if they have a similar molar mass, then obviously an alcohol will have a higher boiling point, because an alcohol can attract or bond using hydrogen bonds, whereas alkanes can only use dispersion forces. Another thing is that alcohols are soluble in water. So the way it works is, if you want to be soluble in water, so water is a polar molecule, so water reacts with water reacts with itself through polar bonds. And so because of that, you need to be soluble in water, you also need to react with one another through polar bonds. So you need to be quite polar to dissolve in water. And so alcohols up to 3 carbons, so alcohols like methanol, ethanol, and propanol are quite soluble in water due to the hydrogen bonding. And alcohols have a nonpolar and polar aspect. The nonpolar aspect is the carbon chain. So the carbon chain, the 3 carbons there, CH3, CH2, CH2, these carbon chains will be nonpolar, right? The only polar part is the OH bond. So the longer and longer the carbon chain of an alcohol becomes, the less and less polar it becomes, because it's the carbon chain, the nonpolar aspect, is a lot bigger compared to the polar aspect, which is the OH bond. So C1 to C3 has comparatively a much larger polar aspect than C4. So because of that, C3 will be more polar than C4, and so it'll be more soluble in water than C4. By C4, I mean an alcohol with 4 carbons in the parent chain, so like butanol plus. So C4 plus is anything like above butanol. And so anything above butanol, the solubility decreases with size as the nonpolar portion increases. So the nonpolar portion is the carbon chain, and so the carbon chain increases as C4, C5, C6, etc. So the main point that you need to take away here is that alcohols, they interact with hydrogen bonding, and so they have quite high boiling points, and we need to supply enough energy to overcome these hydrogen bonds to achieve the boiling, to make it reach the boiling point. And in terms of primary, secondary, tertiary, primary will have a higher boiling point than secondary, which will have a higher boiling point than tertiary. This is because the alkyl groups in primary the alkyl groups in the primary ones are more exposed. So because they're at the end of the chain, or they're primary basically because they're at the end of the chain, the OH group is more exposed, so it can more easily form a hydrogen bond. Whereas with secondary and tertiary, it's less exposed, and so it has a more difficult time forming the hydrogen bonds. And so because of that, its boiling point will be lower. So as the dot point says over here, there's a high extent of the hydrogen bonds forming molecules, and so hydrogen bonding between molecules, and so it will have a higher boiling and melting point. So that is the properties of an alcohol. Now we'll go through a little bit more. So now we'll go through the enthalpy of combustion. So in class, you'll do a prac where you burn a few alcohols under some water and measure the temperature change of the water. And this is trying to calculate the molar enthalpy of combustion and we're trying to find how the molar enthalpy of combustion increases as the alcohols get bigger. So that's essentially the gist of the prac, but what you need to remember is that the molar enthalpy of combustion will increase as the alcohols get bigger. And it kind of makes sense because the larger molecules will have more bonds, and so when you're breaking more of those bonds, you'll release more energy. And so because of that, you'll get more energy per mole. And the molar enthalpy of combustion is given by delta HC, which is equal to negative MC delta T over the moles of fuel that you burned. So yeah, if you did physics last year, then you would know MC delta T. You'd probably know that in chemistry as well. And you just divide it by the moles of fuel that you burned. So let's go through this question now. Question 17. Students were asked to perform a first-hand investigation to determine the molar heat of combustion of ethanol. The following extract is from the practical report of one student. Calculate the molar heat of combustion of ethanol using the student's data. So let's use the formula, right? So we have Q equals MC delta T, M equals grams of water, C equals 4.18, delta T is the change in temperature, and Q will be in joules because we're using 4.18 and grams. So we need to later then convert it into kilojoules and then divide by the number of moles. So let's look over here. So Q equals MC delta T. M is 250. We have over here mass of water over here is 250. C is 4.18. Delta T is, so the final temperature minus initial temperature, 59 minus 19. So we have 40 degrees. So then Q, when we multiply all this together, is 41.8 kilojoules. Now we need to find the mass of ethanol used. To find the mass of ethanol used, what we do is we get the initial mass of the burner and the final mass of the burner, and we minus them together to find the change in mass. And that change in mass is the amount of ethanol that will have combusted. So if we do that, we get 2.3 grams, and we can find the molar mass of ethanol because now we know what ethanol is. So C2H5OH, or it's just, CH3C CH2OH. So we know what ethanol will look like now because we've done IUPAC nomenclature. And so we can find the molar mass of it, and we can, by doing N equals M over M, we can do 2.3 over 46.068 to get 0.0499, and that is the moles of ethanol burnt. So now all we have to do is, we need to find kilojoules per mole. So we know the kilojoules, 41.8, and then we divide it by 0.0499 to get 837 kilojoules per mole. Something that's very important here is you need to be able to know whether it's positive or negative. So although this says 837 kilojoules per mole, the enthalpy of combustion, right? It's combustion. So we're releasing energy into the surroundings. Because we're releasing energy, technically the system itself is losing energy, right? Because it's losing energy to the surroundings, we're releasing energy. So because of that, the answer actually has to be negative. So it's negative 837 kilojoules per mole because it's the enthalpy of combustion, we're losing energy to the surroundings. The system itself is losing energy because we're releasing it to the surroundings. Combustion is exothermic. So it's negative 837 kilojoules per mole. That's something that you should always remember when you're doing enthalpy of combustion. The answer will always be negative. So now let's go through properties of other hydrocarbons like aldehydes. So they generally have an unpleasant odor, and the carbonyl group is polar due to the high electronegativity difference of the C and the O. And the aldehydes, because of that, they can attract through dipole-dipole forces and dispersion forces. They can't interact through hydrogen bonding though, because they don't have a hydrogen bonded to an oxygen or a hydrogen bonded to a nitrogen. And in general, because the CO bond is at the end of the molecule, the compound itself is less polarized than if the C double O bond or the carbonyl group was in the middle of a ketone. And because the aldehyde is less polarized, it can interact through polar bonds less frequently or less strongly than a ketone. Because of this, they have lower boiling points and lower melting points than their ketones. So similar to alcohols, aldehydes with 1 to 3 carbons are quite soluble in water. So methanol, ethanol, propanol are quite soluble in water because they're capable of hydrogen bonding with the water. But C4 plus, so anything like butanol, pentanol, etc., they're less soluble in water due to increasing proportion of the nonpolar section. So as the melting point and boiling point increase, as the melting point and boiling point increase as chain length increases, it becomes less and less polar, and it becomes more and more nonpolar. And so as the carbon chain increases, aldehydes become less and less soluble. And then the final point, melting point and boiling point, these increase as chain length increases, just like I mentioned before. So as the chain length increases, the strength of dispersion forces that it can form increases as well. And so because of that, the melting point and boiling point increase. All right, now we'll go on to ketones. So ketones have in contrast to aldehydes, so aldehydes have an unpleasant sharp odor. Ketones have a pleasant and sweet odor. So the carbonyl group is polar due to the high electronegativity difference of CO bond, again, just like aldehydes. Ketones are capable of both dipole-dipole and dispersion forces. And in opposition to aldehydes, because the C double O bond is in the middle or more towards the middle of the molecule, it is more polarized than the one on the end of the molecule in the aldehyde. Because of that, because it's more polarized, it will have higher melting points and boiling points than the corresponding aldehyde. So in an exam question, you can't just say that because it's more polarized, it's going to have a higher boiling point. You need to be able to expand on this. So because it's more polarized, it can, like the strength of it can form stronger polar bonds. And by forming these stronger polar bonds, it will be able to have a higher boiling point because we'll need to supply more energy to overcome these like stronger polar bonds. And just like aldehydes, C1 and C3 are very soluble in water. C4 plus are less soluble in water due to the increasing proportion of the nonpolar section, because as the carbon chain increases, the nonpolar section increases, and so the compound itself becomes less and less polar, and so less and less able to dissolve in a polar solute like water. However, as the chain length increases, the melting point and boiling point do increase as well. And now we go into carboxylic acids. So carboxylic acids, COOH. So the functional group for a carboxylic acid is the C double bond O bond and a very polar OH bond. So each of these like bonds can form two hydrogen bonds. So the COOH bond can form two hydrogen bonds. Because of that, it will automatically have a higher melting point and boiling point than alcohols. Same with aldehydes and ketones. It will have a higher boiling point than all three that we've talked about so far. So obviously, it will have a higher boiling point than an alcohol, an aldehyde, and a ketone of respective molar masses, so of a molar mass close to it. So it has a high melting point and boiling point, and the only homologous series with melting points higher than carboxylic acids is amides. So amides is the only one that has a higher melting point and boiling point than carboxylic acids. So just like alcohols, aldehydes, and ketones, C1 to C3 are quite soluble in water because it's quite polar at that point. But it gets less soluble after that because as the chain length increases, it becomes more and more non-polar, and so more and more less soluble in a polar solute like water. So yeah, melting points and boiling points increases with size, and the very important takeaway here is carboxylic acids form a stable dimer structure, and this stable dimer structure allows it to like form a very strong very strong intermolecular bonds with itself. And so because of that, we require a lot of energy to overcome the stable dimer structure, or the bonds within the stable dimer structure. And so it gives its very strong or very high melting point and boiling point. The reasons why amides have a higher boiling point than carboxylic acids is because amides interact through another keyword over here, a network of hydrogen bonds. So the keyword over here is stable dimer structure. You always want to include that if you're talking about the boiling point of a carboxylic acid. And if we're comparing with an amide, the reason why amides have a higher boiling point is because of the network of hydrogen bonds within there. So let's look at amines and amides now. So amines, C1 to 2 are gas at room temperature, C3 plus are liquid. So two highly polar NH bonds in primary amine mean they can form two hydrogen bonds. So they have very high melting point and boiling point, but not as high as amides since they also have a C double O bond. So amides can form more hydrogen bonds. And just like before with all the compounds, melting point and boiling point increase the chain length for a similar reason, and it's also quite soluble in water. And this decreases as chain length increases because the non-polar proportion increases as well. So amides. So above C1, it's solid at room temperature. So it's quite, they're quite like, they have very high melting point and boiling points. And a primary amide has a C double O bond and two polar NH bonds, which make it capable of hydrogen bonding. And this means amides have the highest melting point and boiling point of all homologous series. So out of all the organic compounds that we've learned so far, amides have the highest boiling point. And they're the only one with a density higher than water. And just like with all the other compounds, the melting point and boiling point increase with chain length. And they're soluble in polar substances, but this decreases with chain length again because the non-polar proportion increases. And just like I mentioned before, the key word here is that they form a network of hydrogen bonds. That's what allows it to have a higher melting and boiling point than carboxylic acids. So now we go through alkanes. So let's go through unbranched alkanes. So alkanes, let's take unbranched alkanes. So let's go straight linear line alkane, so just an alkane in a straight line. So they can only interact through dispersion forces because they're all nonpolar. So the only way that they interact is through temporary imbalances in charges that occurs within like the molecule itself that causes it to form temporary dipoles. And these temporary dipoles will be attracted to other temporary dipoles between the alkanes, and this will cause it to react with or basically interact with one another through dispersion forces. So this is how it interacts. So it's quite weak, and so because of that, it has quite a low melting point and boiling point. It gets even worse if it's branched. So if it's branched, there's a lower boiling point and melting point because the molecules cannot pack tightly together, and there's also like a smaller contact area between the molecules, and so it'll have an even lower melting point and boiling point. And these branched alkanes will have a lower density as well because they can't pack together as well as these branched or these unbranched alkanes. So the branched one will have a lower density than the unbranched ones because the unbranched ones can like fit together quite nicely. Alkenes and alkynes. So alkenes are more reactive than alkanes due to the electron density of the double bond, but they do have a lower melting point and boiling point than their corresponding alkanes. And this is due to having fewer hydrogens, so they have fewer electrons, which means they have weaker dispersion, or they have weaker temporary imbalances in charge, which leads to weaker temporary dipoles being formed, which leads to weaker temporary dispersion forces. So it's like a cause and effect type thing. Alkynes, so they have a lower melting point and boiling point than their corresponding alkenes, like essentially with the same number of carbons, because once again, fewer number of hydrogens than alkenes, so fewer electrons, fewer temporary imbalances in charges, fewer temporary dipoles forming, fewer electrons, so weaker temporary dipoles, weaker temporary imbalances in charges, so weaker temporary dipoles forming, and so weaker dispersion forces. But once again, as the molecular mass increases, the melting and boiling points increase as well, because obviously the temporary imbalances in charge will also increase as the electron density increases. And it'll also become, these are also insoluble in substances, because insoluble in water, because water is a polar substance, and so this unpolar substance will be very insoluble in polar substances because they can't react with one another through polar bonds. So yeah, the general gist is alkanes have a higher boiling point than alkenes, which have a higher boiling point than alkynes. But it's like swapped around in terms of reactivity. Alkynes have a higher reactivity than alkenes, which have a higher reactivity than alkanes. And because alkanes are because they're saturated, they react through substitution reactions. So what they do is, for a reaction, a substitution is essentially they take away a hydrogen and replace it with something else. For alkenes and alkynes, they go through addition reactions where they break the double bond, and then they open the double bond into a single bond, and then they have to fit the rest of the gaps in the carbon, and so more molecules come to fit those gaps. So yeah, that's kind of the visualization of the difference between a substitution and an addition reaction. So quick bit on haloalkanes. Haloalkanes are capable of dipole-dipole bonding due to the polar CX bonds that they have, because halogens are very electronegative. And so they're quite capable of dipole-dipole and dispersion forces as well, meaning that their boiling point and melting point are higher than their corresponding alkanes. And they're also slightly soluble in water due to this dipole-dipole interaction that they can have, so the polar interaction that they can have with the water molecules. So they're more soluble than alkanes, alkenes, and alkynes, but way less soluble than everything else that we've learned about, because everything else that we've learned about is quite polar. So yeah, homologous series, basically these organic compounds, the trends, right? So melting point and boiling point increase as the molecule gets larger. So an increase in the number of electrons means temporary dipoles are stronger and more frequent, so dispersion forces are stronger. And then solubility decreases as carbon chain gets longer. That's because as the carbon chain gets longer, the nonpolar proportion of the compound keeps increasing until the compound becomes less and less polar. And as it becomes less and less polar, it's unable to react, in terms of the whole compound itself, it reacts less and less using polar bonds with water. And so it becomes less and less reactive or soluble in water. And also larger liquid molecules are more viscous than smaller liquid molecules. So from highest melting point to lowest melting point across all the organic compounds, we have amides, carboxylic acids, alcohols, ketones, aldehydes, amides, carboxylic acids, alcohols, ketones, aldehydes, amines, haloalkanes, alkanes, alkenes, and alkynes. That's just a general gist. If you understand the reasoning behind it, so with amides, the keyword is network of hydrogen bonds. Carboxylic acid, the keyword is the stable dimer structure. Alcohols, the keyword is the hydrogen bonds, etc. So that is kind of the trend. If you remember those keywords, then you should be okay. So let's look at this question right here. So it's a 5-mark question, so obviously we'll have to be writing a lot for this question. So the boiling points and molar masses of 3 compounds are shown in the table. We have acetic acid, butanol, butyl acetate, and yeah, those are the three compounds. They have different molar masses, very different, so varying from 60 to 116, but quite similar boiling points, right? Explain why in terms of structure and bonding of the three explain why these like trends follow in terms of structure and bonding. So looking at this question, the first thing that I'd recommend you doing is whenever you introduce a compound, always put like their respective boiling point in brackets. So this shows the marker that you're actively referring to the data that they provided. So you're saying, if you're saying butyl acetate has the lowest boiling point, full stop, instead of saying that, say butyl acetate has the lowest boiling point of 116 degrees Celsius to show the marker that you're actively referring to the table and using, or like, making use of the information provided. That's just a side note. The main thing that I would look here is, so look at the functional groups, right? One is acetic acid, so carboxylic acid. Obviously, it should have the highest boiling point here because there's no more amides. So we have butanol, so okay. Alcohol, so it should be lower boiling point. And we have butyl acetate, so that is an alkane. Sorry, no, butyl acetate is not an... Oh, actually, it is an alkane. So butyl acetate is an alkane, so it should have a even lower boiling point. So looking at this, right? Why do they have similar boiling points? Acetic acid, carboxylic acid should have a significantly higher boiling point than an alcohol and an alkane. Now, the only difference here that I can see is the molar mass, right? The molar mass increases significantly, going from 60 to 116, and then it clicks, right? So the molar mass is the reason why these boiling points are very similar. So what I would first say is, I would first talk about molar mass and how it does or doesn't impact the boiling point significantly. So in this question, it does impact the boiling point significantly, right? So if looking here, right? So what I would say is the molar mass, the molar mass affects the boiling points of these subjects, of these compounds significantly. And then I would explain how, the electron density, so the greater the molar mass, the greater the electron density, the greater the temporary imbalances in charges that can occur, which means the greater the temporary dipoles that can form and greater the temporary dispersion forces that can form. And due to these greater temporary dispersion forces, the amount of energy needed to overcome these greater temporary dispersion forces increase, right? And because of that, its boiling point also increases. So the reason why it's very similar is due to the increase or the significant increase in molar mass. But, obviously I have to explain it a little bit more. So then I would say introduce a difference in, so after talking about molar mass, I would introduce a difference in functional groups and how that makes a difference. So I would say acetic acid has, how it would interact through the stable dimer structure. I would draw a diagram showing the stable dimer structure. I would show the hydrogen bonds between, carboxylic acid. Same with alcohols. I'd say how they interact through hydrogen bonds, etc. And then I would say, despite the general trend of carboxylic acids having greater boiling points than alcohols and alcohols having greater boiling points than alkanes, in this scenario, they have very similar boiling points due to the effect that molar mass has on it. So the increase in molar mass has this effect, and then I would end the question there. So that's how I would answer it. I would introduce the key concepts first to show the market that I know what I'm talking about, and then I would specifically relate it to the question to answer the question. So unsaturated hydrocarbon. So remember, a hydrocarbon is unsaturated if it could possibly have more atoms binded to it. So obviously a double bond or triple bond makes it unsaturated. So these bonds can flip out and join to other atoms. So the reactions that involve bonds flipping out are called addition reactions. So yeah, that's the difference between an addition and substitution reaction, as I mentioned before. So when these bonds flip out and they bond to other atoms, they're called additions because we add stuff, right? And that's in relation to substitution reactions. So yeah, substitution reactions, what happens is so if we look over here, right? If we look over here, there's a hydrogen over here. We take that hydrogen and we replace it with the chlorine. So we substitute the hydrogen with the chlorine, and that's what makes it a substitution reaction. So going back now, so addition of halogen, typically Br2 and Cl2. Dibromethane is used as a petro additive. So a little bit of background. So let's look at the addition, right? So we have a double bond. It's unsaturated, so we can do an addition. So we can do an addition reaction. So we add the two bromines. we open up this double bond, right? So now there's another gap. So there's two gaps now. So we open up the double bond. There's two gaps for the carbon to be filled. And what happens is this bromine fills those two gaps. So now we get, 1,2 dibromo ethane. Or just, dibromo ethane. So that's what happens. You open up the bond. We also have hydrohalogenase. So the example of this addition reaction is called halogenation, because we take a halogen bonded to a halogen, and then it's an addition reaction between that and an unsaturated hydrocarbon. So it's halogenation. Next, we have something called hydrohalogenation, because there's a hydrogen bonded to a halogen. So it's hydrohalogenation. So again, same compound. We open up the double bond and it gets reacted. H and Br. Next one, hydration. So this is where we add water and it ends up opening up. So it's again another addition reaction, but we open up with the water, right? So if we split up the water now, what happens is we end up forming an alcohol. So we end up splitting it up into OH and H. And this ends up bonding to form an alcohol. So we open up the double bond and then we put in an H and we put in an OH and it forms an alcohol. Now we can go into substitution. So the important thing with substitution is, right, because alkenes and alkynes are quite more reactive than alkanes because because of the presence of the double bond, right? But alkanes are way less reactive because they're already saturated. It's like noble gases. Noble gases are quite unreactive because their electron shells are full. Here they're quite unreactive because they're already saturated, right? So we can't make it go an addition reaction because we can't open up a single bond, right? We can't flip out a single bond, but we can substitute things. And we need an external source of energy to substitute things. So to do this, we use an external source of energy, such as UV light, for example. And we use this UV light to supply the external source of energy. So we're using this UV light, we pluck out the H and we substitute it with Cl. So that's kind of what the substitution reaction here is. So now we can go into the combustion of alcohols. So combustion is an extremely important reason for the production of alcohol. So there's two types of combustion. There's incomplete and complete combustion. So incomplete combustion occurs when there's a limited presence of oxygen and it needs to be heated to ignition temperature. Complete combustion occurs when there's an abundance of oxygen, so everything is going smoothly and everything turns into the proper products. So yeah, we produce H2 and CO2, but for incomplete combustion, we produce H2O and a random ratio or a mix of CO2, carbon monoxide, and just carbon itself. And not all have to be present in incomplete combustion. So yeah, this formula, the bottom two show the results of combusting an alcohol. So you can see over here 2O2 because there's an incomplete insufficient oxygen presence, and 3O2 over here shows the sufficient oxygen reaction, causing it to have complete combustion. Now we have dehydration of alcohols. So what happens is when we dehydrate an alcohol, it turns into an alkene. So if we go back to hydration. So hydration is we take an alkene, we hydrate it with water, and it becomes an alcohol, right? So dehydration is we take that alcohol and turn it back into an alkene. And we need a catalyst for this dehydration, right? So there are a couple conditions what we need for the dehydration reaction. So we need 170 degrees Celsius, so it is endothermic, and then we also need concentrated sulfuric acid catalyst. These are very important that you remember these because you need to always write these down whenever you write a dehydration equation. So you need the presence of heat around 170 degrees Celsius and concentrated sulfuric acid catalyst. What this catalyst does is it lowers the activation energy required and it absorbs the water, and it's also H2SO4 is quite hygroscopic, which means it absorbs the water formed, and this forces the equation forces the reaction to continue and finish. So this is what happens, right? This HOH gets replaced. So we take out the HOH and form a water molecule, and then we replace that, the gap, with a double bond. That's kind of how it works. So now we have substitution with hydrogen halides. So another substitution reaction, we just take the OH and we take out the OH, we form water with it, and we substitute the OH with a halogen. That's kind of what it is. Quite simple. Now we get into oxidation. This is quite important. So we have the oxidation of primary alcohols and secondary alcohols. What's very important is tertiary alcohols cannot oxidize. So primary and secondary alcohols can oxidize, but tertiary alcohols cannot. So the conditions for a primary alcohol to oxidize is we have the oxidizing agent, which is either potassium dichromate or, so we have potassium dichromate, and we also have dilute sulfuric acid, and then we need to heat it under reflux. So in class, you might do the oxidation reaction. It's not guaranteed, but you might do it, and then you'll see what a reflux is, right? So it's like a reflux condenser. And then the last condition concerns whether the oxidizing agent or the alcohol is a limiting reagent. So if we look below, right, if the oxidizing agent is a limiting reagent, the alcohol will partially oxidize to an aldehyde. So this is only for primary alcohols. So the OH will now become a double bond O. But if there's an abundance of oxidizing agent, then the aldehyde will oxidize again to form a carboxylic acid. So that's how it works. So if the oxidizing agent is limited, then it'll form an aldehyde. If it's a limiting reagent, it'll form an aldehyde. But if we add more oxidizing agent now, we will now oxidize the aldehyde to form a carboxylic acid. So assuming you have an abundance in limiting reagent, the primary alcohol will oxidize to form a carboxylic acid. But for secondary alcohols, we can't really do that. So for secondary alcohols, what happens is the OH now forms a ketone. And obviously, we can't turn a ketone into a carboxylic acid because the carbonyl functional group is in the middle of the chain, right? So it can't form a carboxyl or carboxylic acid. So there's only one step here. It goes from a secondary alcohol to a ketone. Now, let's go to alcohol production through substitution. So it's like the reverse of halogen substitution. So what happens is we have NaOH, so sodium hydroxide, and we have a halogen, right? So we have a haloalkane. What we do is we substitute the halogen in the haloalkane with the OH in sodium hydroxide. So by replacing that, we take this and we give it a hydroxyl functional group, making this into an alcohol. So that's what it looks like. NaOH is quite important over here. So in terms of the reaction conditions, the halogenated alkane is heated under reflux with sodium hydroxide in a 50-50 water ethanol solvent. The OH from NaOH substitutes the halogen, producing an alcohol. So now, this is like the industrial means of producing it. So alcohol production via fermentation. So, so the zymase or yeast produces enzymes that breaks down C6H, so glucose, into ethanol and carbon dioxide. So a microorganism such as yeast, which contains enzymes to catalyze the reaction. And there are a couple of things that we need to know. So the nutrients for yeast to use, so we need glucose. And there's a couple of reaction conditions that you need to know. First thing is it has to be moist. So it has to be moist for the yeast to cultivate. Has to be anaerobic, so low oxygen, so that other stuff can't grow. Has to be around 37 degrees Celsius, which is where the yeast become most active. They also have to be sterilized, so it has to be sterilized. And they have to be resistant to sterilization, so that other pathogens can't grow. So yeah, the enzymes in this yeast act as biological catalysts. They produce up to 12 to 15% of ethanol, and anything above this concentration kills the yeast, so the fermentation ceases. So we can only produce about 12 to 15% ethanol using this method. And the low concentration of ethanol can be distilled to increase the concentration above, up to 100%. So we do produce 15%, but we can distill it to make it 100%. So you can also produce alkanes by hydrating alkenes, right? So that's what we learned before. So if we hydrate alkenes, we can produce alcohols. Now we learn about esterification. This is also a practical that you might do in class. So what we do is we add a carboxylic acid and an alcohol, right? We add them together in a flask. So we have in a round bottom flask, right? And we add a few boiling chips and we turn it to boil, right? And we add concentrated sulfuric acid, which is the catalyst. It's also a dehydrator. Basically, what it does is it absorbs the water molecules formed. So you can see over here, through esterification, we form water as a byproduct. What it does is it absorbs the water because it's hygroscopic. So the steps for this is we place the flask in a reflux tube in a heating mantle for 25 minutes. Then we remove the flask, allow it to cool, and we carefully waft vapors towards your nose to record any odors. So there's the esters. They could smell either really bad or really good depending on what you do. Some of them smell quite fruity. The ones in my school, or the ones that I did in my class, smelled quite fruity. So that's something that I remember. And so yeah, what happens is concentrated H2SO4 is used as a catalyst and also a dehydrating agent. So as we mentioned before, the H2SO4 is hygroscopic, so it absorbs water, and is also a catalyst, so it lowers the activation energy. And is heated under reflux because the process of esterification is quite slow. So we need to heat it under reflux to increase the reaction rate, and it also prevents a loss of volatile components. So the carboxylic acid and alcohol and the ester, like the compounds within the round bottom flasks, are quite volatile. So they can like start spitting, right? They can start spitting out of the round bottom flask. To prevent this, we heat it under a reflux condenser. And what that does, it prevents the loss of volatile components. It's very important that you know stuff about a reflux condenser, because this might come up in past papers or in the actual HSC. So that's quite important that you know about the reflux condenser. It speeds up the reaction rate, the fact that we heat it under reflux, and it also prevents loss of volatile components, and it prevents the buildup of pressure that would occur in a closed vessel. So now, the formula for an ester is shown below. Which alcohol and alcoholic acid were used to make this ester? So, if we go back to this now, we can see ethyl propanoate. So we can see, if we look over here, we get ethyl propanoate. So propanoate, so 1, 2, 3, this is the third one. So whichever carbon is bonded to the double bond is the one which has O8 on the end. So you look over here now, carbon is bonded to the double bond, is over here. So let's count this chain, 1, 2, 3, 4. So we should get butanoate. So the ester, the name should be ethyl butanoate. So that should be the name of it. So now if we're trying to answer the question, right? So if we look over here, butanoate. Butanoate comes from the carboxylic acid, butanoic acid. And ethyl comes from the alcohol, ethanol. So the answer is ethanol and butanoic acid, A. We can get this from following this formula over here. Alkanoic acid plus alkanol goes into alkyl alkanoate plus water. So this example is quite useful in terms of finding out and deriving answers like this. Yeah. So now we'll go into polymers, which is one of the final parts. And as I mentioned before in the beginning, polymers is unfortunately a lot of memorization. So going through polymers now. So polymers are essentially large molecules of repeating units or subunits called monomers. So we have addition polymers, which form via addition reactions. So addition reactions we mentioned before, where like the double bond or the triple bond opens up to add more things to it. So that's how addition polymers form. So condensation polymers, on the other hand, form via condensation reactions. So water is always a byproduct of these condensation reactions. So that's something to always keep in mind as well. So that's the difference between an addition polymer and a condensation polymer. And we're going to go through a couple of these. So here, these are a couple addition polymers. So we have polyethylene. So we have high density and low density polyethylene. You'll need to know all of these, by the way. So low density polyethylene. So don't stress too much about memorizing all of this now. Polymers usually come towards the end of the module, so all you need to know is a general idea of like the presence of additional and condensation polymers currently, but you will need to know this for the HSC. So low density polyethylene is where branching occurs, so molecules cannot pack tightly. So because of that, so what happens is they heat it under high temperature and pressure, and so branching occurs, and so the molecules don't pack tightly, and so what happens is it becomes flexible and tough, but it's not strong. So it has a very low has a lower melting point and boiling point than high density polyethylene. And the uses are very important that you know what uses are. It's used for like plastic bags and stuff, and for like the cling wrap, stuff like that. So yeah, plastic bags, cling wrap, and squeezy bottles. High density polyethylene, on the other hand, is produced using a catalyst, and this catalyst means that it doesn't branch as much. So using that catalyst, it doesn't branch as much, and because of that, it's more rigid, durable, and it has a higher melting point and boiling point than low density polyethylene. And because of this, the rigid and durable nature of its properties means that it can be used for garbage bins, buckets, kitchen utensils, natural gas piping, and play equipment. So in terms of the properties, it's very important that you link the properties to the uses. So that's something that's very important. You can't have one without the other. The uses always relate to the properties, and the properties always relate to the uses. So now, let's go into polyvinyl chloride, or PVC, which you might have heard, PVC pipes and stuff. So yeah, it's hard and brittle because of chain stiffening due to large chlorine atoms, but it can be made more flexible with the presence of plasticizers. So this makes it more flexible. Another thing is that CCl bonds, they can degrade in UV light. So because of that, UV blockers and stuff like that are added into the polyvinyl chloride to make it more resistant to UV light. And the CCl bonds mean that dipole-dipole bonds can form between the polymer molecules, and because of that, the presence of these polar dipole molecules mean that it has strong intermolecular forces, and so higher melting point and boiling point. Because of this, it can be used for electrical insulation, garden hoses, drainage and sewerage, guttering, and downpipes. Same with polystyrene now. The big benzene ring causes chain stiffening. So the presence of the big benzene ring over here, it causes chain stiffening. And because of that, polystyrene is also quite rigid and brittle. There's also a few crystalline regions, meaning it's less dispersed, so it can be transparent sometimes. It's a good electrical insulator, and it can also be inflated with hydrocarbon gases to become what we know as styrofoam. And so these trapped gases make it quite low density and a good sound insulator. But this isn't at its rest state. This is after it's been inflated with hydrocarbon gases. So a couple uses are, its rigid nature allows it to be used as tool handles, hard plastic furniture. Its transparent and rigid nature allows it to be used as CD cases. And when it's inflated, it can be used as cheap, lightweight insulator, foam cups, and protective packaging. So if you order something quite big, like a TV or something, it'll probably come packed in styrofoam. And then we have PTFE, or polytetrafluoroethane. So PTFE, it has minimal chain branching, so the molecules pack together very closely, and so it has very strong dispersion forces, so high melting point and boiling point, and has a high strength of CF bonds, making it quite unreactive. So because of the high strength of the CF bonds, the CF bonds don't really want to break, so it's quite unreactive, right? And it's unable to form hydrogen bonds, so it's quite insoluble with water. And because of this, right, it can react quite easily. So because of its being water insoluble, right, so it's unreactive and it's unable to form hydrogen bonds, so it has a high melting point and boiling point. And because of these properties, it's used for non-stick coating on pans. So most of the non-stick coating that you see will be a version or a type of polytetrafluoroethylene or ethane. And it's also used in pipelines to transfer hot chemicals. So that's kind of like how PTFE is used. Now we have condensation polymers. So going through condensation polymers, we have nylon. So nylon 6,6 or 6,6 nylon is the main polymer that you'll be using. And some of these properties are, so the chains are packed together quite closely, and they have high dispersion, high and hydrogen bonds. They're quite rigid, durable, and elastic. They have a high melting point and boiling point, and they have a high degree of polymerization. So they're very long polymers. And this gives it the property of high tensile strength. It gives it, the high tensile strength. And so this high tensile strength allows it to be used for ropes and synthetic fibers, and its rigid, solid, and durable nature allows it to be used in the place of metal bearings. It's also used in machine parts, and it's also used in gun casings as well. And then we have polyester. So polyester most commonly refers to as polyethyl tetraphthalate, or PET. It's quite stable, so it has a highly stable aromatic ring, which makes it inert, so it's very unreactive. And the aromatic ring being quite large means it's quite rigid as well. So it's a quite rigid substance as well, and it's also hydrophobic, so it's scared of water, so it's insoluble in water. But it's very durable, it's elastic, and it's strong. And this nature of it gives it the ability to be inert, rigid, and hydrophobic, so it's quite suitable for packaging foods. And it's also durable, elastic, which means it can be used in clothing. So that is a summary of polymers. So there's addition polymers and condensation polymers. And in terms of the summary that I'm going to give, there's a couple, you need to be aware of the different types of questions that they can give you. So in terms of the HSC, they can ask you to compare the differences between an addition polymer and a condensation polymer. So you need to know at least, you should know all these. So you should know this four and these two. You should know maybe a couple more as well, but yeah. So they can ask you to compare an addition polymer with a condensation polymer. So you need to look at the differences, right? So obviously, one produces water, one is like an addition reaction, one is a condensation reaction, etc. You need to look at the different properties as well. They can also ask you to, in detail, describe the properties of one polymer, so any polymer. So they could specify an addition polymer and a condensation polymer. They could specify like detail the formation and qualities of nylon 6,6, for example. So you need to be able to denote that as well. Another thing is they can also ask you to write a long response on comparing two addition polymers with one another or two condensation polymers with one another. A good thing that I've seen is them asking to compare HDPE with LDPE. So if we go back here, HDPE is high density polyethylene with low density polyethylene. So they're asking us to compare these two. So those are a couple of questions that you should be aware of in terms of polymers. Now soaps. So soaps is the sodium or potassium salt of a fatty acid. It's a long carboxylic acid. So if we look over here in this diagram, this is what a soap will look like. So it has a hydrophobic tail and a hydrophilic head. So hydrophilic means water loving. Hydrophobic means like water hating or like scared of water, all right? So if something is, so grease is quite hydrophobic. So it doesn't dissolve in water because it doesn't react with, like, it doesn't have polar bonds within itself. So it doesn't react with water through polar bonds. And so because of that, it's quite insoluble in water. And so that's why you'll find water not taking away any of the, so if you have a greasy pan, you'll find that warm water or cold water won't take away any of the grease, right? But soap will. So this is how it works, right? So you have the hydrophilic head, so that's soluble in water. So that's water loving. And you have the hydrophobic tail. So the hydrophobic tail, which hates water, but is soluble in oil and grease because it's, non-polar and grease is non-polar. What happens is, so if we look over to this, weird, if we look over to this weird, ball, this gray ball over here, that's a grease molecule, that's dissolved grease. So what happens is when we add soap, the hydrophobic tail of the soap starts inserting itself into the grease, and it ends up looking like this. It ends up looking like a micelle. So this micelle is where the tail, the hydrophobic tails, these soap molecules come together to trap the grease molecule inside a micelle, like a group of soap molecules. And then, because it's trapped itself inside a group of soap molecules, these grease particles can't combine to form like a massive grease blob, essentially, because these micelles have separated the grease particles from one another. And after we've separated the grease particles from one another, these grease dots will start floating in the water now. And now all we have to do is rinse away the grease. So what happens is we add the soap into the water. The soap reaches the grease in the pan, and then the hydrophobic tails, because they hate water, they end up interacting with the grease, and they end up inserting the tails into the grease. And what happens is, after a lot of this soap is attached, the grease molecules begin to lift off the surface. And after they lift off of the surface, the soap molecules clump together to form micelles, and they trap the grease globules within the like a circle or like a ring of soap molecules. So they trap the grease within a ring of soap molecules, and this is called the micelle or gunk sphere, essentially. And these gunk spheres, they start floating in the water now, and because of that, because they're floating in the water and not stuck to a pan or anything, we can just wash them off, and we can just clean the pan. So that's how the process of soaps work. Obviously, in school or you'll learn this a lot more in detail, but in terms of the 2-hour time limit, there's not much detail that we can go to in terms of soaps. But yeah, what you need to know is the process of saponification, which is the process of soaps cleaning stuff, and also the structure of a soap. So the hydrophilic head with a hydrophobic tail. All right, so now we can go through flowcharts for chemical synthesis. So this is how we get between the different homologous series in this molecule. In this module, sorry. So we have the alkane. So if we now put UV light on the alkane, remember what equation that is? That's a substitution reaction, and substitution a hydrohalogenation. So we take away an H using the energy from UV light, and we substitute it with a halogen, and then we get a haloalkane. And then what we do is if we heat it with excess ammonia, the haloalkane, we'll get an amine. If we heat it with reflux and NaOH, so NaOH, this is a substitution reaction as well, what happens is the substitution reaction, we substitute the halogen in the haloalkane with an OH to form an alcohol. And now we can turn this alcohol into a carboxylic acid through oxidation. So we can oxidize this alcohol to turn it into a carboxylic acid. Same way, we can dehydrate the alcohol to form an alkene, or we can hydrate the alkene to form an alcohol. So you can see everything is connected, right? So this, you can form basically everything using anything. So you follow a list of steps to form one another. So basically, so let's say I wanted to form an alcohol using an alkane. What I would do is I would first do a substitution reaction, a hydrohalogenation reaction. So I would shine on UV light, and I would basically take hydrogen or HBr, and then I would take this alkane and turn it into a bromoalkane. So now it's a haloalkane known as bromoalkane. And then I would react it with aqueous NaOH with 50-50 water and ethanol with heat under reflux, and then I would replace the bromo, or like the bromine atom, with an OH atom in the sodium hydroxide, causing it to form an alcohol. So that's how I would get to an alcohol. I'd turn it into a haloalkane, and then I would turn it into an alcohol. Similarly, if I wanted to turn an alkane into a carboxylic acid, I would follow this step, get it into an alcohol form, and then I would oxidize the alcohol into a carboxylic acid, assuming the alcohol that I form is a primary alcohol. So if I wanted to turn a carboxylic acid, if I wanted to turn an alcohol into an alkene, then I would dehydrate the alcohol to turn it into an alkene, and then I could combine it with a hydrogen halide in an addition reaction to form into a hydrogen or a haloalkane. So from an alkene to an haloalkane, we do an addition reaction because it has a double bond. So we open the double bond up and we react it with a hydrogen halide and we turn it into a haloalkane. So everything is quite related. So this is the flowchart that kind of details how we can get through different homologous series in this module that we've learned so far. And with that, we come to the overall summary of this module. So it's pretty content heavy, and IUPAC naming took up the majority of this, especially with like the isomers and everything. But that's essentially the entire module recapped in, or summarized in 2 hours. So the key skills here are differentiating between polymers, knowing the steps of saponification, which we'll learn in more detail, IUPAC nomenclature, because without that you can't do module 8 and module 7. You really need to get down IUPAC naming very well, and also the reactions between organic compounds. So this flowchart here is sure to help you with that. And yeah, a couple reminders. So make sure to check what the sign for your enthalpy values are. So that's a mistake that I made in my exam. When we did enthalpy of combustion, I forgot to put a negative sign there, and I ended up losing a mark in my final answer. So always remember, the enthalpy of combustion, the system is losing energy because we release energy into the surroundings, and so our answer should be a negative value. So yeah, that brings us to the end of our lecture. Thank you for listening through. If you have any questions, please feel free to send them down in the Q&A below. And yeah, thank you for sticking to